Hello, everyone, and welcome to our Shifting Gear with SDV webinar. My name is Amanda, and joining us today is Dana Vede, who will be presenting on the topic of when safety meets open source, building trust in the software defined road ahead. If you have any question for Dana, we move through today's presentation. Feel free to ask in the chat or use the Ask Question tab. Without any further delay, Dana, over to you.
Thank you so much, Amanda. Hi, everybody. Thank you for joining us here today. Good morning, good afternoon, good evening, depending on where you are. I hope you're all set for hearing my discussion here on functional safety. And I'd like to begin with a simple question. It's not a technical one, it's more a human question. Who here trusts software? And maybe you can make use of your raising hand feature, just so we can see if you trust software or not. And going further with that question, do you trust software with your life? Because see, that's a much more difficult question, because trusting software in order to recommend a restaurant, or I don't know, even to finish your sentence is one thing. But in order to trust software to decide whether your car should brake, whether it should steer, or whether it should keep accelerating, that is a completely different story. And yet, millions of people do exactly that every single day, whether they realize it or not, right? So they do trust their own vehicles. For decades, the automotive industry built trust in a very specific way. So cars were mechanical machines. Software existed, but mostly in small, isolated control units. And each ECU had a very clearly defined responsibility. Each supplier owned a well-defined piece of the system. Each safety argument stayed largely inside the organizational boundaries as well. But life isn't simple. It wasn't simple. It was understandable though. Okay. Now, after some time, things changed, and cars have stopped becoming machines with software inside, and instead they started becoming computers with wheels attached to them, right? So today, software practically controls a lot of the stuff within your vehicles. It's controlling braking, it's controlling steering, energy management, driver assistance, connectivity, cloud services, I don't know, artificial intelligence. And increasingly, as you know, those systems depend on open source. Now, for many people, these two words, or better says, two constructions, functional safety and open source, sound almost incompatible, because functional safety sounds more like a discipline, documentation, traceability, very careful engineering, years of validation behind, and so on. While open source sounds more like 1,000 of contributions, continuous evolution, rapid innovation, like really fast, code written across multiple organizations, sometimes even across multiple continents. So normally, people, you, should be asking, can open source ever be trusted in safety critical system? And I'd actually argue that this would be maybe the wrong question. The real question would be, how do we build this trust? Because trust is ultimately what functional safety has always been about. It's not about bureaucracy, not about the paperwork, not about certification. It's about trust. So today, what I'd like to show you is how that idea is evolving, and why I believe that open source isn't weakening functional safety, but in fact, it's forcing us to rethink how trust itself is demonstrated. Oops, apologies. And just a little bit about myself to to explain to you why this topic has become such a personal interest of mine. So I've spent roughly 25 years working in the automotive software part of the industry. And during these years, I've had the opportunity to experience almost every perspective out there. So I've written software, I've tested software, I've managed software projects, I've worked in the quality assurance area, I've defined engineering processes, I've spent countless hours discussing requirements or reviewing defects, arguing about the traceability, and trying to make complex development organizations work together properly. So I've seen functional safety from the inside, not as an academic discipline, but as something that affects the everyday engineering decisions. And today, well, for some years already, I'm working at the Eclipse Foundation, which means I'm now spending my time in a rather different environment. Instead of one company, one supplier, one OEM, I'm surrounded by communities, right? By people from competing companies working together, building shared infrastructure together, sharing ideas, sharing code, sharing responsibility. So at a glance, that seems almost incompatible with your traditional functional safety thinking. But over the last few years, I, for one, have become convinced that this is not the case. In fact, I believe open source can strengthen many aspects of the engineering quality, provided that we stop trying to force it into organizational models that were designed decades ago. And this is actually the journey that I'd like to take you on today. So here's how we're going to spend the next 40 minutes, roughly. We'll begin by establishing a common language, because whenever people discuss functional safety, they often assume everyone means the same thing. And in reality, they rarely do. So we'll start with the fundamentals, what functional safety actually is, and perhaps more importantly, what it isn't. And from there, we'll briefly look at the standards, not because I want to teach ISO 26262, that would take far longer than 40 minutes, but because those standards explain why the industry works the way it does. After that, we'll move into what I think is the really interesting part, which would be software-defined vehicles, artificial intelligence, continuous deployment, over-the-air updates, centralized computing, all of these technologies that fundamentally change the assumptions behind the traditional automotive engineering. And once we've established that, we'll ask the difficult question: how does open source fit into all of this? And can collaborative development produce software that is suitable for safety related application? And if so, what has to change? And finally, I'll share some of the work that we're doing at the Eclipse Foundation, and not because we've solved every problem, we certainly haven't, but because I believe we're beginning to develop a new way of thinking about engineering evidence, governance, and ultimately trust. So let's begin at the beginning. What exactly is functional safety? Um, Before we talk about standards, before we talk about open source, about software defined vehicles, we need to answer one simple question: why does functional safety exist at all? Because if we don't understand that, everything else will just become paperwork. The ISO 26262 that we all know of simply becomes paperwork, and the safety cases of your projects, the reviews, the traceability, everything becomes just paperwork. And none of these things that I enumerated already, so safety cases, reviews, the traceability, none of these exist for their own sake, right? They have a reason. They all exist because at some point, a human being may depend on the decisions that our software makes. And that's where the story actually begins. Okay. So uh, when people first hear the words functional safety, they usually imagine software that practically never fails, It's perfect software. Well, that's not the case. It's impossible. There is no bug-free software. So as we know, software fails, hardware fails, sensors may fail, communication buses may fail, the power supplies may fail. Eventually, anything and everything may fail. And the automotive industry has learned this lesson ages ago, decades ago, but not because engineering lacked skills, but because the complexity is always the ones that wins in such a system. And if you build something sufficiently complex, one day something unexpected will happen. And the question is not so much whether this is going to happen, but how exactly will the system function? So what happens after something out of the ordinary happens? So just imagine you're driving home one evening. It's raining, visibility is poor. You're driving on a motorway at a motorway speed, and suddenly the steering angle sensor begins producing incorrect values. What would you want your vehicle to do? Would you want it to continue operating, pretending everything is fine, or would you rather it recognizes the problem? I don't know, warn you as a driver, reduce the functionality if necessary, and remain controllable. Normally every person chooses the second option because you want to be safe, right? That's what functional safety is. And notice here something important. Functional safety doesn't promise perfection. What it promises is predictable behavior. That is the profound difference there. The objective of functional safety is not to eliminate every failure. It's to eliminate the dangerous behavior that might come with the failure. And there's one misconception uh, that people normally have. Um, and one that I would like to challenge here, and the fact that sometimes people confuse reliability with the safety. So they look at two, let's say two vehicles, and they consider if the vehicle is reliable at the same time it's safe. Well, it's not always the case. But in this example that I took with two vehicles, let's just imagine it for a moment. So let's say vehicle A never fails until one day that without any warning whatsoever, out of the blue, it suddenly accelerates unexpectedly while you're driving. While vehicle B, from time to time, detects sensor inconsistencies. So it's not perfect, it just detects all sorts of inconsistencies like in your sensors functionalities. So it enters a limp home mode. It's sort of like a debug mode, if you want. It's a safer mode without all the complex functionality that you would normally have. And then after entering the limpo mode, it's asking the driver to visit the workshop, right? And then it completes the journey safely. So out of these two, which ones would you trust? The vehicle A or vehicle B? Because the interesting part is vehicle B is actually less reliable. It experiences more faults, right? But it's significantly safer because it already knows how to fail. So in case something happens, it goes into the limpo mode and directs you to the nearest workshop to take care of the issue. So it is safer. So I think that's the one of the most beautiful ideas in engineering. The good engineering isn't demonstrated when everything works. It's demonstrated when something goes wrong and the system still protecting people. And there's a safe sentence that I often use when discussing functional safety. Safety is an actual claim. It may sound unusual, but think about it. Whenever an engineer says this system is safe, they're making a claim, right? And here comes the difficult part. Can they prove it? Can they demonstrate with evidence that the system behaves safely under failure? Because that's ultimately what functional safety is: evidence supporting a safety claim. And I'd like you to keep that phrase in mind, because we'll come back to it later, much later, when we start to discuss about open source. And another phrase that I would like for you to give a little bit of focus, that I have on the slide right here, is invisible success. And what I love about this expression is that it really shows what's hidden. As it says, invisible. So think about your journey to work today, in case you work in an office. Did anyone congratulate the lift for stopping at the correct floor? Most probably not. Did anyone thank the ABS module in your vehicle for functioning correctly last week? Probably not. Um, so safety is pretty much invisible. You are sort of expecting it, and if it works, there's nothing dramatic happening. You simply arrive home or wherever your destination was, right? But the absence of safety could lead to a catastrophe. Is actually the greatest compliment that safety engineers can receive, that there's no catastrophe happening, there's nothing happening there. That means your functional safety within your system is actually functioning. So again, functional safety is not about perfection. It's not about eliminating every bug. It's not about making your systems immortal, but it's about ensuring that when reality surprises us, our systems respond calmly, predictably, and safely. That is the real definition of functional safety. Now let's have a look about at how we actually achieve that. Broadly speaking, failures comes in two flavors. The first is random. So physical components wear out, electronic devices age, connectors corrode, I don't know, resistors drift, mechanical parts eventually break. Is just physics. We can't negotiate with physics. It's just stuff that happens, right? But software is different. Software doesn't become tired. Software doesn't age, as in, well, it might age, but it probably ages like fine wine, as in, it doesn't, nothing happens to it because it ages. But if software fails, it's usually because humans have introduced a mistake somewhere. So perhaps the requirements were incomplete. Maybe two components interacted unexpectedly. Maybe someone misunderstood an assumption during the design. Perhaps a corner case wasn't tested fully or properly. These are what we call systematic failures. So not random ones, but systematic ones. They're particularly dangerous because they can affect every product built from the same software. So if your software produces systematic failures, it's not going to produce those failures only on one of the vehicles that it resides on. It will produce those failures on every vehicle that software resides on. So one defect would translate into millions of vehicles with defects. So how do we defend ourselves in such conditions? We don't rely on hope. Okay, that's the first thing. We build mechanisms. Sometimes we duplicate critical systems. So if one processor produces an unexpected answer, maybe another processor can detect the discrepancy. Sometimes we continuously monitor ourselves using watchdogs, doing health checks, doing plausibility checks, doing good running diagnostic routines, and the system is constantly asking itself, does this still make sense? Imagine a pilot flying an aircraft while continuously checking every instrument. Modern vehicles increasingly do the same thing. They are continuously validating their own behavior. It's just they do that through their own automatic mechanisms. You don't have to keep an eye on each indicator within your vehicle on your displays and such. The vehicle would do that for you. However, eventually, one of those mechanisms may conclude that, quote unquote, I no longer trust the information that I'm receiving from whatever corners of that system. So here comes the most important decision. Do we continue or do we stop? Most people instinctively think stopping is always safer. Actually, that's not true. Imagine your engine is simply switched off while trying to overtake a lorry on the motorway. Would that be safe? I'd say that wouldn't be safe at all. So, safety isn't about stopping, it's about entering what engineers call a safe state. Okay. So, sometimes that might mean reduced performance. Sometimes it's handling control back to the driver. Sometimes it's gracefully degrading the functionality. Sometimes it's executing an emergency stop. So the correct safe state depends entirely on the context. And that's why functional safety is so fascinating, because it's not simply engineering, it's engineering, but combined with risk management, combined also with human behavior. And this leads us to perhaps the single most important sentence in today's presentation. Functional safety isn't about preventing failure. Functional safety is, though, about preventing failure from becoming harmful. Okay? Remember that sentence, because everything else, ISO 26262, ASIL levels, your typical safety cases, whatever open source governance that we might get into, our trustable software framework, everything else exists to support that simple single objective: protecting people. Everything else is just a means to achieve this objective. And now that we understand the problem, let us look at the engineering framework the automotive industry created in order to solve things. Okay, so let's see how the industry itself came to some solutions through key standards and frameworks. So we've established why functional safety exists. Now the obvious question would become, how do thousands of engineers work together to achieve it? Because saying build a safe system is easy, but actually proving that the system is safe is something entirely different. The automotive industry realized very early that good intentions weren't just good enough. Safety couldn't depend on individual brilliance. It has to become repeatable, it has to become predictable, it has to be auditable. And that is why standards in the direction of functional safety were born. They were not invented in order to replace engineering, but rather to make good engineering reproducible. Now, whenever functional safety is discussed in in automotive, in whatever initiatives related to automotive, one standard inevitably appears, and that's ISO 26262, because that's the dedicated functional safety standard for the automotive industry. And for many engineers, that name immediately brings to mind really thick documents, tons of checklists, loads of hours spent in reviews or audits, and mountains of traceability evidence. But what I'd like to suggest is a different way of thinking about it. Imagine you're building a bridge. Would you simply tell your construction company, build me a safe bridge? Because obviously you need for it to be safe. Whenever you cross the bridge, you need it not to fall. Whenever you're under the bridge, you need it not to fall on you, right? So you need it to be safe. But do you tell the construction company, just build me a safe bridge? Of course not. You'd be expected to bring them calculation, to design, to review their designs, to do independent verifications, to test materials, to do inspections, to have evidence. So the bridge isn't trusted because somebody says it's a safe bridge. It's trusted because all the engineering process that is applied behind it produces convincing evidence that the respective bridge is safe. And ISO 26262 as a standard applies exactly the same philosophy to software intensive vehicles. Now, one of the most elegant concepts within the standard is that safety begins long before anybody writes the code. It begins by asking a deceptively simple question: what could go wrong? It does not begin with how do we implement this feature, but rather, if this feature behaves incorrectly, would there be any harm to anyone? Or who could be harmed? And that is a completely different mindset, as you can feel. The standard then introduces a structured reasoning process. So first, identify a hazard, then evaluate the associated risk with that hazard, and finally, determine how rigorous your engineering process needs to be. And that is where your ASIL comes in the picture. That is automotive safety integrity level for everybody. Um, a lot of people, while doing presentations on functional safety, spend a long time explaining ASIL A through ASIL D. Well, I'm not going to do that because it's not the ASIL part that I think is that interesting. What I think is interesting is why different systems deserve different levels of confidence. So, as an example, an infotainment screen freezing for a few seconds is inconvenient. A braking controller behaving unexpected, unpredictably, is potentially catastrophic. So, naturally, these two systems, your infotainment screen and your braking controller, shouldn't be engineered in exactly the same way, because one is I would say more uh, could potentially be more harmful than the other. So the level of engineering rigor should reflect absolutely the potential consequences of that particular component. So that one is one of the most sensible principles in the entire standard, in my view. People also sometimes think that ISO 26262 is trying to certify software, which it isn't. What it's trying to do is trying to provide confidence in the engineering process that produced the respective software. So, and this is an important distinction because software changes, your requirements evolve, bugs are fixed, vehicles receive updates. Confidence, therefore, comes from consistently applying a disciplined engineering. It's not coming from believing that one particular version is somehow perfect or better than another version. It's this confidence in and consistency in applying those disciplined engineering processes. You'll also notice a brief reference in the presentation to IEC 61508. Think of it as the pattern, as the parent of many domain-specific safety standards. It established many of the core principles that later evolved into standards for automotive industry, for railways, for medical devices, industry automation, and many other safety critical industries. Um, and the details in each differ, but the philosophy remains remarkably consistent throughout the whole thing. So identify risk, reduce risk, provide evidence with the ultimate goal to protect people. Moving on now to, oh, sorry. In the actual engineering life cycle and in a practical context, if ISO 26262 tells us what needs to be achieved, how do engineering teams actually organize themselves to achieve it? And this is what brings us into the engineering life cycle. Many of you have probably seen the V model before. I'm sure of it, either from your waterfall experiences, from your ASPICE experiences, and so on. And some of you may even have unpleasant memories of it because it's often criticized for being old-fashioned, rigid, waterfall, right? Slow. Uh, I personally think that's an unfair criticism because I don't believe the V model is primarily about project planning. You see, I believe the V model, it's about something much more fundamental, meaning traceability. Every requirement exists for a reason. Every design decision supports some requirement. Then every implementation realizes some design or some design decision. Every test demonstrates that something actually works. So everything is connected. Nothing exists in a complete isolation. All of it is connected. And that is the true beauty behind the V model. It's an engineering map. It's not a project management methodology. And why is that so important? Because imagine you're investigating an accident, okay, a vehicle that collided, and someone asks, why does this line of software exist in your vehicle? Can you answer that? Can you point to the requirement that ultimately led to having that line of code? Can you identify the design decision that led to that line of code? Can you show the verification evidence saying that line of code is doing what it's supposed to do? And if the answer is yes, then you have traceability. And if the answer is no, what you have is uncertainty. And uncertainty is something functional safety is trying very, very hard to eliminate, right? This is also maybe a good moment to mention something relatively newer, which is SOTIF, the ISO 21448 standard. At a first glance, that sounds almost identical to functional safety, but the problem it addresses is subtly different. Traditional functional safety assumes something has failed, a sensor, a processor, a communication channel. SOTIF, though, asks completely different questions. It asks, what if nothing has technically failed, but the system still makes the wrong decision? Imagine an AI-based perception system. Okay, every sensor works perfectly. The software contains no obvious defect, but it makes a shadow, but it mistakes a shadow for an obstacle, let's say. Or it just fails to recognize a child that is partially hidden behind a parked vehicle. So nothing is broken, and yet the behavior is unsafe. And this is exactly the kind of challenge that SOTIV is trying to address. As vehicles become increasingly intelligent, those scenarios become increasingly important. And another point that's often misunderstood, and I briefly hinted on that, is certification. People frequently imagine that ISO 26262 actually certifies software. No, it doesn't. What it certifies is the confidence in the development process. That's why your documentation, reviews, configuration management, change control, testing, verification, traceability, all of that matter. They are not just administrative overhead, okay? They are engineering evidence. And I'd like to connect this back to something we discussed earlier. Remember when I said safety is a claim? Well, the engineering life cycle is how we support that claim. As I said, every review, every test, every requirement, every verification activity adds another piece to the evidence. Eventually, all those pieces come together into something that we call a safety case, which is a structured argument explaining why we believe this system is acceptably safe. Notice the wording, okay? Not perfectly safe, acceptably safe. Because again, engineering is always about managing risks and it's never about eliminating it entirely. Now, to get a bit of practical context to the whole thing, um, moving on now, because everything that we've discussed so far has been rather abstract. Let's try to make it a bit more real. So take, for example, the anti-lock braking systems. The ABS doesn't prevent components from failing. If a wheel speed sensor becomes unreliable, the system detects that. It doesn't continue pretending everything is normal. Instead, what it does, it disables the anti-lock braking, falls back to a conventional hydraulic braking, and informs the driver. So the feature is degraded. Safety is maintained through doing that. That is how functional safety is seen in action. Or consider another example. Consider power steering, electric power steering. Imagine the steering motor begins behaving unpredictably. Would you want your software continuously applying steering corrections? Of course not. Instead, the system disconnects the assistance. So the steering becomes heavier, but you as the driver remain in control. Again, performance is sacrificed in order to preserve safety. The same principle appears for far beyond the automotive. So I don't know. Think about elevators. Most people imagine the lift cable snapping, for example, because for some reason Hollywood loves that scenario. You've seen it in many movies, probably. Modern elevators are actually designed with multiple independent safety mechanisms. So if overspeed is detected, mechanical brakes engage automatically. And again, the objective isn't to prevent every conceivable failure, but rather to ensure that no single failure becomes catastrophic. What else? Industrial cobots, so collaborative robots, right? Unlike your traditional industrial robots, they intentionally share the workspace with humans. And this is only possible because they are continuously monitoring their environment. So the moment they detect unexpected human presence, they stop. And that's not because the robot has failed, but because they are designed, engineered to protect people, and this always takes priority over completing the task. Okay, By now, you've probably noticed a pattern. So, different industries, different technologies, different standards, different engineering teams, and yet exactly the same philosophy everywhere. Detect problems early, understand the risk, design predictable behavior, provide evidence, and all with the purpose of protecting the people. Everything we've discussed so far has one thing in common. It assumes engineering happens inside relatively stable organizational boundaries. A supplier develops software, an OEM integrates it, certification follows, traceability is largely contained within that ecosystem. But what happens when software is developed by hundreds of contributors across dozens of organizations, changing every single day? And that's where our story is going to take a fascinating turn, because that's exactly the world of the software defined vehicle. And since we are into that, everything we've discussed so far works remarkably well. In fact, modern vehicles are among the safest machines humanity has ever built so far. And it's not because they are simple, it's quite the opposite. They are incredibly complex. But we've become very good at engineering that complexity. Okay. However, the automotive industry is now undergoing one of its biggest transformations since the invention of the assembly line. And that transformation isn't necessarily the electric vehicles, and it's not necessarily the autonomous driving, not even the artificial intelligence. All of these are actual consequences. The real transformation is that the car has become a software platform. And once software becomes the primary product, many of our traditional engineering assumptions begin to change. So, in going in this direction, let's take one example: the ADAS systems, so the advanced driver assistance systems. Today, we take features like automatic emergency braking, lane keeping assistance, adaptive cruise control. We take all of these features almost for granted. They've become the normal, right? But think about what they are actually doing. They're continuously observing the world and making decisions and predicting human behavior. Sometimes they act faster than the driver. That would have sounded like science fiction 20 years ago, right? But today, it's just becoming ordinary engineering. And yet, there's something interesting. When these systems work well, people often attribute that success to artificial intelligence, right? Or sophisticated algorithms, or I don't know, powerful processors. I don't know. I for one attribute it to engineering discipline, proper engineering discipline, because none of those technologies matter if they haven't been engineered responsibly. Let's look again at the automatic emergency braking. The interesting question isn't, can it detect an obstacle, but rather, what happens if it fails detecting an obstacle? Or perhaps even more importantly, what happens if it thinks an obstacle exists when it actually doesn't? So now we're back into the world of functional safety, predictable behavior, defined limits, graceful degradation, safe states. So exactly the principles we've already discussed. One of the things I admire most about systems such as Volvo City Safety or Toyota Safety Sense isn't that they are technologically impressive. It's that they demonstrate restraint. Good safety engineering isn't about making systems more aggressive. It's about understanding what their limits are, knowing when the automation should intervene, knowing when it should hand control back to the driver, knowing when uncertainty has become too great. And all of that takes discipline, not just intelligence. And nothing, notice another thing, none of these decisions can be improvised after the software has been written. You can't suddenly decide, oh, perhaps the vehicle should behave differently during sensor lifetime. Those behaviors are designed from the very beginning. Those are architectural decisions. So that's why safety has to be considered from day one of you creating your product. It's not. I like to make use of this expression. It's not like the pinch of salt you add in your food at the end, right? You have to add it from the beginning, because if it doesn't um, go across all the ingredients of your product, you're not going to have it consistently, right? So those behaviors, as we said, are designed from the very beginning. They are architectural decisions, and that's why safety has to be considered from day one, not added shortly before the release or before the audit or before going to a certification body. Um, Now, I'd like to address something that's often misunderstood, especially outside of the automotive industry. Whenever a highly publicized accident occurs, the immediate reaction is often the software failed. But if we investigate serious incidents, we usually discover that something much more complicated is happening there. The software may have behaved exactly as it was programmed. The real failure occurred somewhere else. Perhaps the requirements were incomplete. Perhaps assumptions about human behavior were unrealistic. Perhaps the testing never considered a particular environmental condition. Perhaps multiple individuals um, um, multiple individuals' decisions were acceptable, um, and yet interacted in an unexpected way in your whole system. These are all system failures, not software failures. Just to make it very clear, this is a very important distinction. So my slide here mentions incidents such as the 2018 Uber crash and the widely discussed misuse of driver assistance systems. Rather than focusing on assigning blame, I'd like us to focus on the engineering lesson that they offer. In almost every major engineering accident, aviation, space exploration, railways, medical devices, automotive, the conclusion is remarkably similar. Rarely does one defective component cause a catastrophe on its own. Usually, multiple small weaknesses align. It's an assumption here, a misunderstanding there, a missing validation activity over there, an unexpected human action over here, and eventually the entire system behaves in a way that nobody intended for it to behave. And that's why functional safety has evolved into systems engineering rather than just software. So we're no longer validating individual components, we're validating interactions between components. There is also another challenge that we must acknowledge. Uh, Human beings, we are wonderfully creative. So not only when designing systems, but also when using them. So sometimes drivers misuse the technology, sometimes intentionally, sometimes accidentally, sometimes simply because they are tired or distracted or maybe overconfident. Engineering, therefore, cannot assume ideal users, right? We must design and engineer for real people, right? So we need to take into account their flaws as well, their mistakes, and that's the somewhat uncomfortable truth, I would say, but it's essential to our engineering processes as well. So if there's one message that I'd like you to remember from this side, this particular slide, is this: the biggest safety risks rarely come from spectacular technical failures. They usually come from ordinary assumptions that nobody thought to question. Okay, looking a bit more into the software defined vehicle revolution, arriving at last at the real reason why we're here today. 'Cause everything we've discussed, like ISO 26362, functional safety in general, the V model, traceability, safety cases, was largely developed during an era where software looked very different. A typical vehicle contained dozens of electronic control unit, um, each responsible for one specific function. One supplier developed one ECU, another supplier developed another ECU. Integration certainly wasn't easy, but responsibility were relatively clear and helped with the actual integration process. Now that picture is disappearing because the modern vehicles are increasingly replacing dozens of specialized controllers with a handful of extremely powerful computing platforms. So instead of many small brains, there will be one very large brain. That's incredibly attractive from an engineering perspective because you get more flexibility, you get simpler hardware, you get software defined functionality, you get continuous improvement. But what it also does is it creates entirely new challenges. And this is the interesting part. If multiple critical functions now execute on the same computing platform, how do we ensure that they cannot interfere with one another? How do we isolate the failures? How do we guarantee the timing? How do we demonstrate the independence, like complete independence? And these questions that barely existed before are now becoming central architectural concerns. And then there's the software itself. Traditional automotive software evolved slowly, but evolved. The major releases were separated by months, sometimes years. Today, many manufacturers aspire to deliver over the air updates every few weeks or even more frequently. So just think about what that means. Our software becomes better continuously. That's wonderful. But every update also changes the evidence supporting our safety argument. Every modification raises a new question or a new challenge. Has anything safety related changed? Have the previous assumptions that we made remain valid? Have new interactions emerge? So did we bring in a new component? Do we need to emphasize new interactions with the new component? So safety engineering therefore has to become much more continuous. It cannot be just a snapshot where you pull all your evidence together when you do your release and then you're headed to your certification body. Evidence can no longer be produced only at the end of a project, which, by the way, was never uh, a good practice to begin with, but it's just the way things have evolved. So evidence must evolve together with the software. And then on top of everything else, there's artificial intelligence. This is perhaps the most fascinating challenge of them all. Traditional software behaves deterministically. Given the same inputs, we expect the same outputs. And this is what has driven many industries, in particular the automotive one. Given the same inputs, we expect the same outputs. Neural networks, however, don't always provide the same kind of transparency. They may perform brilliantly, no question about that. Yet explaining why they reached a particular conclusion, it can be sometimes extremely difficult. And that's not necessarily a flaw, but it does challenge many of our existing engineering techniques. So, as I said before, we we were expected to have the same behavior, right? Now we don't have this anymore. So we need to adapt the techniques within our engineering processes so that we embrace this way of working as well. So how do we validate behavior that we cannot easily explain? How do we build the confidence? How do we establish the evidence? All those questions remain active areas of research across the industry, and not just in automotive, I would say. Now, well, I'd like you to notice something. Everything we've discussed over the last few minutes, centralized computing, continuous deployment, AI usage, frequent over-the-air updates, shared software platforms, all of them have one thing in common. Software is no longer produced by isolated teams working behind closed doors. It increasingly depends on collaboration, right? Across suppliers, across OEMs, across technology providers, across open source communities. And all of that brings us perhaps to the most provocative question of today's presentation. If the future of automotive software is collaborative, what does functional safety look like in a collaborative world? Let's talk about open source. Up until now, we've talked about functional safety as if the software were developed inside clearly defined organizational boundaries. One company, one engineering process, one management structure, one chain of responsibility. Well, that model has served the industry remarkably well, but software no longer evolves like that. Increasingly, the software inside our vehicles is built collaboratively, as said, across the different suppliers, different OEMs, across countries, across communities. And that is naturally raising an uncomfortable question. Can we, through collaborative software development, ever satisfy the demands of functional safety standards? And the immediate instinctive answer that many people have is no. And I think that's because they are asking the wrong question. So let's begin with a simple observation. Open source isn't coming to automotive. It's already here, okay? The operating systems, maybe you're familiar with Redux, for example, the middleware, the networking stacks, the development tools, the build systems, container technologies. Large part of the modern automotive software ecosystem already depend on open source in one way or another. So this slide in particular illustrates this with examples such as Linux, AutoWare, Apollo. So the debate isn't really about whether open source should exist, and in particular within the automotive industry, because that discussion has already been settled by reality. But the real question is, how do we engineer it responsibly? Okay, and that keyword there is responsibly. And one of the biggest misconceptions that I encounter is the belief that proprietary software is somehow automatically safer. No, it isn't. I mean, closed source doesn't eliminate defects, it simply makes them less visible. Likewise, open source doesn't magically improve quality. Making source code public doesn't guarantee good engineering. So, a transparency alone isn't evidence. Discipline, however, is. So, please note that distinction. It's an important one. Um, and in that context, people sometimes quote Linus's law: "Given enough eyeballs, all bugs are shallow." It's a wonderful phrase, and I like it very much. But I'd be careful not to interpret it too literally, because large communities don't automatically discover every defect, nor do they automatically produce safety evidence. However, they do create opportunities for independent review, for broader expertise, for faster identification of defects, for collaborative improvements, opportunities. And those are the real engineering advantages. The challenge is converting those advantages, those opportunities, into something that satisfies the requirements of functional safety as standards. And this is where the cultural mismatch appears. So traditional functional safety grew up inside organizations. Requirements belonged, as we discussed before, to one company. The design reviews happened inside one company. Configuration management belonged to that one company. Responsibilities were very clearly defined. However, open source looks very different. Contributors work for different employers. Some contribute in their own spare time, so not even on behalf of their employer. Others as part of commercial programs. People join, people leave. The repositories of the different projects evolve continuously. The governance replaces the hierarchy that you normally have within an organization. So, at a first glance, it seems it's almost incompatible with the classical safety thinking. But perhaps we're making an incorrect assumption here. Perhaps we've been assuming that safety depends on organizational structure. I, for one, don't believe it does. I believe safety depends on the actual discipline, engineering discipline. Those are not those two things are not the same. So your discipline with your structure are definitely not the same. Um, Imagine two projects. One is completely proprietary, poor documentation, minimal review, weak testing, little traceability, and the other is developed openly. Every discussion is recorded, every review is visible, every design decision is archived, every test is reproducible, every change is publicly traceable. Which project would you trust out of these two? And instinctively, most engineers choose the second one. And now notice what happened. You didn't choose based on the licensing. You chose based on evidence. And it's exactly the same principle we've been discussing since the beginning of this presentation. So perhaps open source isn't the obstacle. Perhaps it simply forces us to rethink how engineering evidence is produced. And from that perspective, let's take a little look at how we start thinking about this, about the problem in this way. So the next question naturally becomes, how do we help open source communities produce that evidence in a consistent manner? And that's where the Eclipse Foundation has been investing significant effort, not by reinventing functional safety, but by adapting good engineering practices to collaborative development. Um, from that perspective, what I'd like to underline is that people usually, when they hear open source governance, they often imagine licenses, contribution agreements, legal processes, all those things matter. But from a functional safety perspective, governance means something much deeper. It means creating an environment where the engineering decisions are becoming visible, repeatable, and auditable. So, three aspects there: visible, repeatable, auditable. And the slides contains contrasts of the traditional proprietary silos with a more transparent meritocratic model that aims to produce the measurable artifacts and governance evidence. Now, historically, many organizations viewed safety as something internal. So the processes were designed around the company boundaries, evidence stayed inside the company boundaries, audits happened inside the company boundaries. Now, the open collaboration changes that, as said already. The communities need mechanisms that allow people from many organizations to work together while still producing trustworthy engineering outputs. And that's a governance challenge as much as it is a technical one. And one example in that direction is Eclipse Redux. Many of you already know it is a real-time operating system, but what interests me isn't only the technology, it's the engineering discipline around it. Open development doesn't mean uncontrolled development. It's quite the opposite. It requires clear contribution rules. It requires transparent reviews, repeatable release processes, documented decisions. Without those large collaborative projects, they simply don't scale. Um, you'll also notice on the slide that there are some references to maturity badges. I like these because they shift the conversation away from marketing claims. Instead of asking, is this project good? We ask, what objective evidence supports our confidence in this project? So that's a much more useful engineering question. The badges don't create trust. Evidence creates trust. But the badges simply communicate the presence of that evidence in a structured manner. Now, everything we have discussed today leads naturally to this one slide. Remember our definition from the beginning that safety is a claim? Well, if safety is a claim, then we need evidence. And if we need evidence, we need a systematic way of organizing that evidence. And that's exactly the role of the Eclipse Trustable Software Framework. As my slide explains here, and you'll be able to review it afterwards, TSF is a framework for evaluating risk in continuous delivery by structuring claims and evidence through tenets and assertions, making trust measurable and auditable. Notice something interesting here. TSF doesn't try to replace ISO 26262. It doesn't compete with any of the existing standards. Instead, what it does, it completes them. Think of it as an organizing framework, okay? A way of expressing confidence through structured arguments rather than isolated documents. I sometimes compare it to constructing a legal case, okay? A lawyer doesn't walk into the court carrying one decisive document. They present many pieces of evidence, like witness statements, expert testimony, physical evidence, I don't know, sometimes historical content. Each individual piece may be insufficient, but together they create a convincing argument. Engineering confidence works remarkably similar. So there's no single test that proves safety, no single review that proves it, or single process that proves it. The confidence actually emerges from the accumulation of the evidence. Now, think about modern software. Thousands of commits, hundreds of contributors, continuous integration, automated testing, security scanning, code reviews, static analysis, issue tracking, community discussions. All of those activities already produce evidence. And the challenge isn't the creating of the evidence. The challenge is organizing it, connecting it, making it understandable, making it auditable. And that's why I find TSF so exciting, because it acknowledges that modern software engineering already generates enormous amounts of information. And instead of asking engineers to produce entirely new artifacts, it helps transforming the existing engineering activities into that structured confidence. And I'd like to make one final observation before we move to the conclusion. Everything we've discussed today, governance, traceability, engineering discipline, structured evidence, isn't really about open source. It's about engineering maturity in general. Okay? Open source simply makes that maturity visible. Which brings us to one final question: is if evidence is more important than ownership, what does that mean for certification itself? Um, and from that perspective, I'd like to finish our whole talk by discussing two words that are often used almost interchangeably: compliance and certification. I want you to understand that they are related, but they are not the same thing. Um, Compliance is continuous adherence to standards through governance and evidence, while certification is an independent confirmation that a particular version conforms to defined requirements. Now, imagine you've just graduated from university. Your diploma tells the world that at a particular moment in life, you successfully completed a recognized course of study. It's valuable because it opens doors for you, right? People trust that you've met a certain standard. But here's the interesting question: does receiving your diploma guarantee that you'll still be the best engineer 20 years later? Of course not. You have to keep up with the novelties, right? So what really matters over those 20 years? It's learning, it's experience, it's your continuous improvement, it's your professional judgment, it's evidence that you've continued developing. So certification is a little like that diploma. It provides the confidence that at a particular point in time, you have fulfilled those requirements. So it's important. Sometimes it's essential, but it isn't the whole story. Now, think about how software evolves nowadays. A modern software defined vehicle doesn't remain frozen after it leaves the factory. It receives updates, right? SOTA updates that we discussed about, security fixes, performance improvements, new features, sometimes every few weeks. So every change raises a new question. Does the original certification still tell the whole story? Or do we need fresh evidence? And that's where compliance becomes far more dynamic. Compliance isn't a one off event like certification, it's an ongoing engineering discipline. It's the continuous demonstration that our development process remains trustworthy as the software evolves. I'd like to challenge a common misconception here. Sometimes organizations begin treating certification as the objective, as if the goal were simply to obtain that certificate. I don't believe that's why functional safety exists. The objective has never been to collect certificates. The objective has always been to protect people from harm. So certification is one way of demonstrating that confidence, but it is not confidence itself. That's the distinction that I wanted to make. And now let's connect this to open source, because many people ask, can open source be certified? Well, that's certainly an interesting question, and I'm pretty sure we've already shown that yes, we can certify open source. The Eclipse ThreadX project already responds to that question, but I'd rather ask a more interesting question here. Can open source continuously produce trustworthy evidence? So what do you actually need in order to go for certification? Because in a world of continuous deployment, continuous integration, delivery, collaboration, the continuous evidence becomes incredibly valuable. So it's perhaps even more valuable than periodic snapshots of your project. uh, Evidence-based trust outweighs near compliance steps. This is what I would like you to remain with from the slide. Yes, certificates create confidence, and evidence sustain confidence, but the evidence-based trust outweighs the mere compliance steps. Okay? And looking into the future of safety and collaboration, where does all of this leave us? We've established that open source is already part of the modern automotive software. We also established that functional safety remains absolutely essential, and that software-defined vehicles require more continuous engineering than ever before. So what happens next? Okay. I'd like to introduce you now to the idea of treating open source components as safety elements out of context by surrounding them with appropriate validation and integration practices while acknowledging the challenges that exist, such as liability and traceability. And I think that's a very pragmatic way of looking at the problem instead of asking whether an open source component is intrinsically safe. Um, so instead of that, we should rather ask, how should it be integrated, that particular open source component? What assumptions are we making around it? Um, is evidence already available, and what is that evidence? What additional evidence do we need to produce? And that's exactly the kind of engineering thinking that functional safety encourages. Of course, the important challenges still remain, like the liability, the long-term maintenance, the contributor accountability, traceability across the distributed development. And these are not trivial problems. They are genuine engineering and organizational questions. So we shouldn't pretend otherwise. But here's something I'd like to emphasize. Every major transformation in engineering has introduced new questions. Electric, electric propulsion did, the cloud computing did, artificial intelligence certainly is doing that, and open source is no different. So the presence of unanswered questions doesn't mean the approach is flawed. It just means that our engineering practices need to evolve. So one of the things that I appreciate most about functional safety that it's never been static. The industry has continuously adapted. Hardware became software, software became distributed software, distributed systems became connected systems became software defined. So the principles remained, it's just the engineering that evolved. And I believe we're witnessing another one of these moments, not the replacement of functionality. Um, it's the next chapter. So if I had to summarize the future in one sentence, it would be this: innovation moves quickly and trust must move with it. If trust cannot evolve as rapidly as innovation, eventually the innovation will slow down. And it's not because the engineers are lacking ideas, but it's because society doesn't get confidence in those innovative approaches. So our responsibility is to make sure that this is not happening. And I'd like to finish now by returning to the question I asked at the very beginning. Who trusts software with their life? after after these well, more than almost an hour, I hope the answer has become a little clearer for everyone. And absolutely, if we don't trust the software because it's proprietary, we don't trust software because it's open source, we don't trust software because somebody tells us it's safe, we trust software because skilled engineers using designed discipline processes produce convincing evidence, and that it behaves safely when people depend on it. Not eliminating certainty, but managing it, not preventing every failure, but preventing failures from becoming harmful. And perhaps that's the biggest lesson that I hope you take away today. Open source doesn't reduce our responsibility, it increases it, because collaboration at global scale requires even greater transparency, even stronger governance, and even better engineering discipline. And that is it from my side. I hope you enjoyed the presentation, and I'll be taking any questions if you have any.
Thank you, Dana, for this presentation. And as she mentioned, if anyone has a question, you can please drop it to the chat or the question tab. So it's the bubble with the question mark on it. Also, we are looking forward to more shifting gear with SDV in 2026, so this year. So if you're interested in presenting, feel free to fill out the form, which I will link right now to the chat. There we go. Let me link it now. Ah, there's great. We have some nice comments, Dana. So if you feel like doing something amazing like Dana just did, please fill out the form. And also, finally, if you have any feedback on this program, we'd love to hear from you. We are always trying to improve our webinar. So I'm going to share with you our survey that will appear now. It's the green button just there for the survey. So please feel free to fill it out. And also, so if you don't have any question, I would like to thank you again, Dana, for this presentation. It was more than an hour, but definitely worth it. I think everybody is going away with something today. And if we don't have any question, we'll end the session. You will receive, of course, the replay by email in the next 24 hours. So thank you again, everybody that attended to the meeting, and we wish you a wonderful day.
Thank you so much. Thank you, Amanda, for everything. And thank you guys
Thank
for
you.
being here today. Thank you.
Thank you. See you soon.
Bye bye.